which is minimize sum over t. Theta over here is, what is theta over here? So what are the network parameters? So you can see them in the previous equation. So this is B, W, U, C, D. These are the layers, weights of the layers and the bias parameters. Is there anything else? Nothing else. So the parameters are B, W, V, C, and C. These are the parameters. Okay, so that's my loss function. And how, where is the dependence of L on the parameters? You can just see it over here. If you just expand L, so you can write it as yt y hat t, and y hat t is dependent upon all of these v, c, w, u, v. So y hat is basically a function of theta. When you write it out, you will see that this LT function depends on theta. Right. So the objective is, if you want to train this network, you want to compute the derivatives of this loss function with respect to each of these parameters. Right. So basically, I want to compute this. This is unknown. Delta V is unknown. When I want to do the training of the network, these are all unknown. Delta C, delta U. These are the 5 gradients that I need to know to do gradient descent, stochastic gradient descent, to train this network. I will be given this sequence. So during training, you will be given x1, x2, x tau, and the corresponding outputs, true outputs, y1, y2, y tau. That's your training data. And given this data, I would like to just minimize the objective function. So if you remember, we also saw that this objective function is nothing but the, let's see what it was. So it's nothing but, you can think of it as the maximum likelihood. So maximum likelihood objective is, what are you given over here? You're given over here the x1s to xt's. So I want to predict yt. Right. So here is your objective. I want to predict at every instant. I want to predict yt given all the previous. I'm sometimes using these time instances as a subscript. Sometimes I'm using them as superscript. So just being sloppy. Classification using neural network. So this is for one particular output at time instant t. This is what you want to minimize. Minimize the minus the log of p theta yt given. So why is yt given all the previous inputs? Because you can see that At one instant, at the YT, I want to maximize this probability or minimize the negative log of this probability. I want to choose theta such that I maximize this probability. This was uh, actually the base rule, if you remember. So YT basically depends on all of the X keys through history. That's why I don't condition on only XT. I condition on all the X keys before XT because they are coming into picture through the history. Right? So this function is basically, we had done this exercise. So this function is basically exactly if you write down, this is going to be uh, what we had on the previous slide. YT log of 1, right? And if you want to do it for every time step, you have to sum it over t. So there are multiple ways to arrive at this loss function. One is that we did it directly because we had already gone over cross entropy loss in detail, and we studied how to take this maximum likelihood objective and get to this loss function, right? So you can, it must be clear that this loss function is nothing but the maximum likelihood. That's where it is coming from. Okay, now the next question is that I should start thinking about how to find out these gradients, because this is what I need to do to, to train the network using gradient descent. So I just want to go over how to compute these gradients for these recurrent neural network ones. We have done this computing gradients for a dense feed-forward neural network, but recurrent neural network is a little bit different from dense. So I just want to quickly go over how to compute these gradients. So before that, let's just uh, see how what would be the gradient calculation. How the gradient at one particular state of this layer, how would they depend on the previous states? So you can see that the unfolded, from this unfolded version, you can see that to compute particular output O, you have to basically, the network has to sequence through. It will take x1, compute h1, then x2, compute h2. It has to sequence through all the states, and then it should predict the final output or t plus 1. So the feed forward of the network, basically, if you have tau stages, feed forward through the network takes order tau time. Means that I need basically the output of the previous state to compute the next state. I cannot compute the next state before I have gotten the value of the previous state. So I have to wait until the previous state is available, and I use it to compute the next state. So it's going to take order tau time steps to compute the next, to entirely go through the network. Okay, so that's one thing. So the network is inherently sequential. Similarly, this is the feed forward. So if you remember from the gradient calculations, let me see what are the comments. Entire setup. I have an iPad which is connected to a Mac. Then it is wired. Then there is a Google Meet. Then there is this hands-free. So too many things.
Anyways, let's continue. So, as I was saying, this network is sequential. And so, if you remember from the gradient calculations that we did for the dense network, we had, for example, gradient, if I remember, gradient W, gradient with respect to W of the loss function L over there was something like, I'm only going to write uh, approximately what I remember. It was something like this. There was a transpose term, and it was multiplied by if this was Lth layer, it was the L minus 1. So this is basically when you compute y hat, you have to take a forward path through the network. So we took a forward path through the network to compute y hats, then we subtracted it from the true labels, transposed it, and then it was back propagated through, I think it was L plus 1. Yeah. It was back propagated through some layers, all the layers which are in front of WL. Yeah. So gradient calculation always is can be decomposed into a forward path and a backward path, backward backward flow and forward flow, right? So in each case, when you take a forward pass through this network, it's going to take order tau time, and backward pass is also going to take order tau time. So this we want to, so this is going to be problematic, not problematic, but it's going to slow down the training process. So what I want to do is, for example, to train this, uh, to train for W, I really need to go and back propagate through all of these stages. We'll write the gradients and you will see it. So I want to, if you want to speed up the training, and if your application allows it, then probably you don't want to have this sequential nature over here. So there will be a different formation of this network, which instead of using this history over here, because this is history to history recurrence, which is making this network sequential. Instead of doing this, we can directly feed the previous label, true label, into this history. I'll motivate it later, but just keep it in mind that this network is sequential, which is going to make the training a little bit slower because it has to back propagate through all the stages for the gradient calculation. Anyway, so before I move on, let's just compute all these gradients, one of these gradients. Uh, so here, I think I missed delta BL, gradient BL. So delta W, gradient with respect to W, gradient with respect to E, gradient with respect to B, C, and U. I want to compute at least one of these so that you have an idea how this back propagation is working in this case, or what is the chain rule and all. If you remember, when we computed gradients, we started off, even when we went over the chain rule, the first step was to write down the first step was to compute make a variable dependence graph, right? And using that variable dependence graph, we were able to write down the chain rule very easily. So we are going to do a similar exercise over here. So let me first give you, so the gradient conventions used in this book are a little bit different from what I used in my handouts. So I'm just going to start by writing the gradient conventions that are used over here. So let me give you an example. Suppose you have function z, which is, sorry, you have a variable z, which is mapped, which is mapping, the function g is mapping y into z. Y is a vector, z is a scalar, and then there is another function which basically maps an x into y. So we're going from x through a function into y, and then using another function into z. Z is a scalar. Okay, so what I want to do is I want to compute the gradient or the derivative of z with respect to a component, ith component of this vector. So x has components of x or x1, x2, x3. So this, using chain rule, we have already gone over it. This function, this derivative is simply sum over j partial yj over partial xi into partial z over partial yj. Right, so basically we have two hops between x and z. So every entry of y is dependent on every entry of x, because this function could be anything. And then all of the entries of y are mapped into z. So for one particular, so you can think of this like this. The entries of y, every entry of x over here is influencing every entry of y through this mapping. And then since z, the output variable z has just one, it's a scalar value. So this is the graph, variable dependence graph, whatever y. So there are like multiple paths that lead z to any x. So that's why we have this summation. Okay, so if you stack these variables up and I want to compute partial z by partial x with respect to the entire thing, which is partial z by partial x1 up to partial z by partial xd, or whatever is the dimension of x. This is then just equal to, using these formulas, if you stack them all up, you will see that this is equal to partial y over partial x transpose, and then partial z over partial y. So now whenever I use these arrows, these are now vectors. So this is, so what is partial y over partial x? In this case, partial y over partial x is, so if y is, for example, rk, x is rn, the partial y over partial x will be a matrix of dimension rk by n. And partial z over partial y, that will belong to, I think it should belong to, let's see. Let's write it. I want to use a different notation for this. Let's write it. Gradient yz. So gradient yz, which is which is basically partial y or partial z transpose, I guess. So partial y or partial z is, sorry, partial z or partial y. So partial z by partial y is, let me move to this, let's write over here. Partial z over partial y is belonging to R one by n, no, RK, 1 by k. And the gradient yz is just the transpose of it. So it is RK by 1. Okay, now you can see that all the dimensions match. So this is now, since it's k by n, so this transpose will be n by k. And this gradient is already, I've showed you, this is k by 1. So then you multiply these two things together. So this thing is going to be of the dimension of n by 1. So it would be better to also denote this by, just to keep it consistent, by like this, gradient x with respect to z, right? Because this is always a column vector gradient. Right over here, it is a column vector of length k. Length of this column vector is determined by the variable with respect to which you are taking derivative. Z is a scalar. So over here, you're taking a derivative with respect to k, x, which is of length n. So you can see then you multiply n by k and then k by 1, it's going to be n by 1 vector. So that's the one convention that we are going to use when we are going to compute these derivatives. In general, if you have the function f, sorry, if you have a function g, which maps a matrix y into z, and then you have another function f which maps a matrix x into y, then the gradient with respect to x of z, z is a scalar, z belongs to R, is sum over j gradient x yj into partial z by partial yj. So we are going to be basically use, this is just a generalization of the previous formula. Of this formula, right? Yeah. So previously we had this formula. So it's a generalization of this particular. So we have these two, and I'm going to be using these two formulas to compute the gradients. Okay, let's take a pause over here. Okay. Now, let's now start by computing the gradients. It's a simple calculation. Let's start. So first, as I mentioned, I want to first draw the variable dependence. How these variables are dependent on each other. So this was these were the equations that we just wrote. So let's draw a variable, how these variables depend on each other. So I'm going to try to make it as clean as possible. So AT depends on BW, HT minus 1, U, and XT. Then you go into HT, and then you go into O. So like, so HT only depends on AT as it is clear from equation 10.9 that we just wrote. OT depends on three things: C, V, and HT. And finally, Y hat T just depends on OT. And after that, the loss function LT, that depends on Y hat T and the true label YT. Okay, and the L depends on all of these LTs from all these stages. You will have inputs coming from LT minus 1, sorry, LT plus 1. There will be another graph like this for LT minus 1 and so on. So the final loss function is sum of all these loss functions. That's the variable dependence graph. Since each state at time t is dependent upon the previous state through the history vector, so there is another thing that we should be careful over here, which is determined by this equation. This equation is AT equal to B plus W HT minus 1 UXT. I should erase it. And then this means if I rewrite this same equation at time t plus 1, it becomes B WHT plus UXT plus 1. That's the same equation at time t plus 1 because the network is the same from time to time. Right, so this equation basically shows us that we have to create HT also impacts the next state, right? HT doesn't only impact its current output, OT, it also impacts the next output, right? So we have to be careful about that. We have to, that's the main difference between variable dependence in this graph and the dense neural network. Here, HT is also impacting the next state. So I have to draw that variable dependence too. So HT goes into AT plus 1 as it is clear from this equation. And then AT plus 1 is dependent upon, again, W, B, U, and XT plus 1, right? And all of this is dependent on HT plus 1 as it is. You will see there is also an equation like this, right? Which is just like the previous state. Always AT plus 1, you apply a hyperbolic tangent function and then compute the HT plus 1. And then you go into OT plus 1 just as above. And that is dependent on V and C. And finally, you again have Y hat T plus 1. Just like in this above graph, OT goes into YT, so OT plus 1 goes into Y hat T plus 1. Let me make it a little bit cleaner. And then it goes into the loss function LT plus 1, which takes input from Y hat YT plus 1. And that output goes over here into the total loss function. Okay, so this is the variable dependence graph. Now it basically, I just draw it because I want it to be clear how the variables are dependent on each other. Okay, so let's pause it over here. I want to go back over here and give you an example of these two scenarios in action. These two and computing the derivatives. Let's just think like take y to be w x plus b. I'm just making up an example to depict. So this you can think of, this is z is equal to, what were we denoting it by? F. Z is equal to gy. So this is your gy function, this norm. And so this is your y is equal to fx function, right? And as we derived that gradient of x with respect of z with respect to x is basically nothing but partial y partial x transpose into gradient of z with respect to y. Okay, and this is, so I have to first compute partial y over partial x. This is, as we have mentioned in the previous definition, this is just the, so ith jth, so this is going to be a matrix whose ith jth entry, the ith jth entry of this matrix is just partial yj over partial xi. So if this is the equation that relates y with x, what do you think y partial yj over partial xi is going to be? This is just going to be, you can write it out, the jth entry of y is jth row of w with x multiplied by x. So if you take the derivative of this row with respect to only the ith entry of x, so all u is just going to pick off wij. That's the ijth entry of w. So this entire matrix whose ijth entry is just the ijth entry of w, so this entire matrix is just going to be this w matrix, right? So that's the w matrix, and then gradient, what is gradient with respect to y of z? That is simple. So this is partial z over partial y1, partial z over partial y, whatever is the dimension of y. That's called just d. So this is just basically, you can compute it, we have done it before. So this is just y itself. Okay, so if you plug in these two things into this formula, this tells us that this gradient is w transpose y. So this is just an example of that formula. Okay, you can see all the dimensions agree. W transpose y is nice. It's gonna, its dimensions agree with y. So you can multiply them, and the resultant dimension is a column vector, which is the gradient of z with respect to x. So this is just an example. Now let's get back to this particular graph that we had. I will now start off by computing. For example, I want to compute this. I want to just show how to compute the gradient of L with respect to W. So let's start to do that. There are multiple hops through which we'll have to so since this L was just a sum over T LT, so I have to compute the derivative of this L with respect to this W. So I'll first compute partial L over partial LT, then partial LT over partial OT, and partial OT over partial HT, and then like traverse all the way back to W. That's what I'm going to do. So basically, I have to take this loss function, and I have to see how does it depend on W. It depends on W through this path, and it also depends on W through another path. Sorry, I have to show this path to you. It depends on W through this path. Then it also depends on W through this path, right? So I have to see all of these dependencies, compute all of this. There is another path as well. So let's see, it's going to be a little bit messy. So let's start. So partial L over partial LT. What is this? This is just 1. I'm not going to explain it. It's very simple to see. And then partial L over partial OT. The I here to here, we have computed this leg. Now we have to go from here to, we have to go one step back into here. I have computed this leg. I have to now go over here. So partial I over here represents the ith component of the output at time instant t. So this is just partial L by partial LT into partial LT over partial OTI. And we have done this in the previous handout. Exactly. This loss function is just the cross entropy, and I'm taking its derivative OT, which is related to this cross entropy node through a softmax. So from OT to L, sorry, from you can see that how was OT related to from OT to L, from these two are related to a softmax. We had exactly this scenario in our previous handout, and we saw that these derivatives basically come out to be the predicted label minus the true label. So we had done this. I'm not going to do it again. So, and then partial L. I'm just moving backwards. Partial L over partial HT. What is behind OT? It's HT. So this is just going to be, so now this is exactly the scenario that we covered in the last page. L is a scalar valued function or a variable, and HT is a vector, right? And we saw that if HT and L are related through some intermediate variable OT, this is exactly this scenario where you have X which is related to Z through an intermediate variable Y. So I want to compute the derivative of Z with respect to X. So this is exactly this scenario over here, partial L over partial HT, and the intermediate variable is OT. So if you apply just the previous expression that we just derived, it is just going to be transpose partial L over partial OT. That's your exact same formula that we just had studied. So what is this partial OT over partial HT? So I want to emphasize over here one thing, that this chain formula that I have written over here is saying that the derivative of HT of the loss function with respect to HT is given by this formula. It only applies to the one of the time steps that I'm going to clarify in a second. Anyways, first you shall tell me what is partial. What is this? Partial OT or partial HT? This thing is, anyone who has the answer, you can type it in. So let's see the equation. It should be clear from the equation. How is HT related to OT? It is related through this matrix V. So when you're going to take the derivative of these two together, this is exactly the scenario that is in the example that we just did. So this is going to be just V. All right, so this thing is then just going to be V transpose partial L over partial OT. I'm just going to denote it by the gradient. I shouldn't even denote it by partial L over partial OT. I should just write the gradient of it. And I should write this to be gradient with respect to HTL. Okay, so this is the derivative. Let's take 2 minutes pause and you can ask questions. We did take the derivative. So we did this in the previous handout. So I didn't repeat it, but all the loss softmax stuff is covered in this. So the cross entropy term is covered in this. And it's going to eventually, when you just write these out, it's going to give you this thing. So we had done this in the previous handout and we had gotten exactly the same result, so I didn't repeat it. So if you don't understand it, go back to the last handout, the one that I wrote. Okay, so I think this is going to be it. I'm just going to continue next time from